Great, thank you. Yeah, hi, I'm Aliza Beverage, and I'm a fifth-year PhD student here at Berkeley. And I'm going to start my talk off today by motivating why we care about metals and what metals can tell us about quiescent galaxies. So the first thing we can learn is about chemical enrichment. What regulates the metals in galaxies? The second one is past star formation. And that's because when we measure the metallicity of quiescent galaxies, we're actually looking at the metallicity of the gas in stars, the metallicity of the gas in stars, not of the gas just in the ISM. And the gas in stars reflects a record of the past star formation. The third thing we can learn about is quenching. Metals can clue us into about how slow or how quick a galaxy stops forming its stars. And finally, we can learn about merger history or assembly history. And that's because of the unique fact of quiescent galaxies that by definition, they're no longer forming stars. And so when a quiescent galaxy stops forming stars, its metallicity is locked in place, and it's not going to change over time unless other stars are added to the halo, either through mergers or late-time star formation. So by tracing the metallicity of quiescent galaxies over cosmic time, we can actually learn about the merger history and the assembly history of this population. Speaking of which, what do we know already about the lower redshift universe? So here are stacks of SDSS galaxies. So there's hundreds of galaxies contributing to each point there. And we're looking at the chemical compositions of the stars, not of the gas. X-axis is the velocity dispersion, which you can think of for the means of this talk as just a tracer of the stellar mass. So what we find for the SDSS massive quiescent galaxy population is that more massive galaxies are more metal rich. They have shorter star formation timescales, so they form their stars rapidly. And we know that because we can use the alpha to iron ratio, so the ratio of alpha elements to iron peak elements as a tracer of the star formation timescale. And finally, we find that more massive galaxies, they're older. And so we have this picture of galaxy formation in which galaxies that are more massive form their stars both earlier in the universe and over much shorter timescales than less massive galaxies. But this picture is kind of incomplete because we're trying to understand the formation of galaxies that stopped forming stars like 10 billion plus years ago, and it's hard to imagine that these galaxies haven't experienced mergers or late-time star formation that's affected these trends or messed them up. So by going to higher redshift, we can first confirm whether this story is indeed the case, that this story of galaxy formation is actually what it is. And second, we can learn if these trends are different at higher redshift, if they evolve, that evolution tells us something about the buildup of the massive quiescent galaxy population over time. Okay, so that's the stage at lower redshift. What about higher redshift? What do we know about quiescent galaxies and their chemical compositions at maybe a redshift greater than 1? Haha, I set you up for that one. We actually don't know because we have not measured these trends yet. And the reason for that is because these measurements are extremely difficult. So to show you why, here is a simulation of two galaxies, same mass. One is star forming, one is quiescent. And immediately it's so clear why this is. We have booming emission lines for star forming galaxies from which we can measure metallicities out to very far distances. But for quiescent galaxies, we're only left with these little wiggles in the spectrum, which you might not even be able to see. So we need ultra deep spectra. The other thing is when we blow up the spectrum, even if we get these amazing spectra, we see that they're really complicated, which is great. We have a lot of information, but it's also hard to model. And for that reason, we've only measured the mass metallicity relation for quiescent galaxies out to a redshift of around 0.7, whereas for star-forming galaxies, it's been measured out to redshifts greater than 3. So we want to learn about these quiescent galaxies. How are we going to do that at higher redshift? Luckily, we have surveys that are ongoing or finished, which are going to reach these higher redshifts. So x-axis here is redshift. I just talked about SDSS, and I'm going to just very briefly mention the legacy survey, which was a survey of 4,000 quiescent galaxies with VMOS on the VLT at redshift of around 0.7. These spectra are ultra deep, and I selected about 135 of these galaxies that were quiescent. And to show you how great these spectra are, I split them into 4 bins of velocity dispersion, and I stacked them. And here are those spectra. You might be like, oh, are those just the models you just showed me? No, this is real data. Pretty incredible. All these wiggles are real. And the other thing you might notice is that they look very similar. This is very subtle work. And you really can only see the differences in these 4 different spectra when you take the different spectrum. So now we see that, for example, the magnesium line gets deeper as you go to higher velocity dispersions. So with these beautiful spectra, I was actually able to constrain 11 elemental abundances, which is kind of absurd. And here they are. Well, the lines aren't showing up, but here they are. I split them into 3 different categories based on their nucleosynthetic channels. Y-axis is the abundance for all the elements. We also looked at the elemental abundance ratios, which tells you something different about the galaxy, and specifically its star formation history and chemical enrichment. And I don't have time to get into these results, but I encourage you to take a look at our paper from this year. I do want to just highlight, though, like, it's pretty incredible that a decade ago we were barely measuring stellar metallicities at this high of redshift, and now we have elemental abundances for 11 elements. That's pretty cool. Okay, so this is where we stand at intermediate redshifts. How about even higher redshifts? So here is the current state at redshift greater than 1. The black line is the redshift 0 and 0.7 results. Iron abundance on the left side. The middle panel is magnesium over iron. And the last one is the age corrected for the aging of the universe. And these 1, 2, 3, 4, 5 points are the only existing measurements for galaxies, for elemental abundances of individual galaxies. And that's kind of sad. So luckily we have Keck, and specifically the Keck Heavy Metal Survey. And the goal is to fill in this abundance diagram. So that brings me to the third survey with heavy metal. That's the name of the survey, because we're looking for heavy metals. And we have this fun text that we use. And so we have a total of 21 massive quiescent galaxies between a redshift of 1 and 2.5. And the galaxies were selected from an overdense galaxy field, which means that we were able to fit all 21 galaxies into only 4 Keck pointings. And so each of these pointings, we go super deep, 17 to 30 hour total integration per pointing. And that's split between LRIS and MOSFIRE. And that translates into a rest frame wavelength coverage of key absorption features that we use to measure the abundances. So here are 4 example spectra. They're a little noisier than the legacy spectra, but like for this redshift, this is pretty incredible. The red lines are our best fit models. So we can capture all these little wiggles. And we model the spectra using a full spectrum modeling code called ALF, which assumes variable abundances. And here are our results. So this is the state of the field before, and now with the Keck Heavy Metal Survey, we're starting to really fill in this diagram. And I'll say, like, the uncertainties are quite large on these individual measurements, and also sample sizes are pretty small, but we're starting to build this picture of the quiescent galaxy population at higher redshift, where they are more iron deficient than the lower redshift quiescent galaxies. They're slightly alpha enhanced, especially at the higher redshifts, the green stars. And they formed extremely early. This last point is actually kind of understood just by realizing that the age of the universe at higher redshift was much younger, and so the galaxies in that universe are also younger. Great. So now I want to look at the average abundances at each redshift, now that we have 4 different time steps, basically. So these are 1 point per time step for per redshift interval. Now the evolution over time, where x-axis is now redshift, is much easier to see. But what does this evolution mean? Well, remember before I said that the alpha to iron ratio tells us something about the star formation timescale of galaxies. So here I'm using magnesium as a tracer of alpha abundance. And by comparing the elemental abundances at each redshift interval to just a very simple chemical evolution model, we can start to learn something about the star formation histories of these galaxies. So I did just that. And these are the inferred star formation histories. So now the x-axis is time, and the y-axis is star formation rate, normalized. And what we see is, it's pretty striking, the higher redshift galaxies here, a typical galaxy at redshift 2, formed extremely early and very rapidly compared to the SDSS galaxies. Now, this actually kind of makes sense because we're selecting galaxies that are quiescent at redshift 2. By default, we are requiring that those galaxies formed extremely early and are already quenched. And so this kind of just is an observational bias, whereas at later times, we're looking at galaxies at redshift 0, they had much longer to become quiescent. And so they're going to have formed on average later and over longer timescales. But if that is all this is, like the only reason we see evolution is because of this observational bias, then these galaxies here in redshift 2 should evolve passively. And if that's the case, then we should find them in the SDSS survey or in lower redshift surveys. So now I'm going to look at now I'm going to look at the individual galaxies. So here is a sample of SDSS quiescent galaxies in the low redshift universe, and also the galaxies from the massive survey at much higher masses. And when we overplot the heavy metal galaxies, we see that about half of them have chemical compositions that are not present in the SDSS and massive surveys. And what that means is that this passive evolution alone cannot explain our observations. These galaxies here do not appear at later times, and therefore something has to happen to them in order to increase their iron abundance and decrease their magnesium over iron ratios. Minor mergers can't do this because minor mergers will move them in the wrong way. The answer we have come up with to explain these observations is that we require major mergers and or late-time star formation, possibly triggered by major mergers, to bring these galaxies into agreement with the lower redshift individual measurements. Okay, so again, I'll just note, uncertainties are large, we have small sample sizes, so these observations will really benefit from even more galaxies and more measurements. And luckily, we have a JWST program where we are targeting 16 massive quiescent galaxies between redshift 1 and 2.5 with near spec. And again, we were able to find 16 galaxies in a single pointing of JWST, which is incredible. And then we were able to fit them into all the little slits. And we are going for 16 hours, these are ultra deep spectra. To show you how great these spectra are, I simulated our faintest target. And here's a simulation for 16 hours of near spec for a very faint target. And pretty incredible, we were easily able to see all the absorption features, and we can very easily fit a model to those. So one great thing about this survey is not only are we going to increase the sample size by quite a bit, we're also going to be reaching to lower stellar masses, and so therefore we can start to constrain the trends as a function of mass at these higher redshifts, and that compared to lower redshift trends, like I said in the beginning, is really going to help us understand the buildup of the massive quiescent galaxy population over time. And with that, I'll leave my summary slide, but I will say that the heavy metal survey papers, they were working on them, and they should be on archive in the coming weeks, so keep an eye out, and I'll take questions.